Hello, I would like to welcome you to an introduction to astronomy. This is lecture 2, How Big, How Far, and How Fast. This is from chapter 1 in the Essential Cosmic Perspective. At the conclusion of this lecture, you're going to be able to describe the sense of scale in the universe. You're going to identify the different units of measurement used by astronomers to determine that scale. And you're also going to describe the concept of look-back time and how it applies to astronomical distances. So without further ado, let's look at the scale of the universe. The first thing you must realize is whenever you start talking about scales of the universe, especially how big, how far, you're not going to become familiar, or you're not going to be able to apply this to anything that you can put into a little box like you know in everyday life. Okay, so what you've got to realize is you're going to be dealing with some astronomical distances. I got jokes. Okay, so there's just big numbers. Okay, so what we've got to do is we've got to take those large numbers and actually make them smaller. So the first thing you have to realize is space is big. As quoted by Douglas Adams here, it's big, really big. You just won't believe how vastly, hugely, mind-boggling big it is. I mean, you may think it's a long way down the street to the chemist, but that's just peanuts to space. Okay. Of course, one of the greatest astronomical movies of all time, The Hitchhiker's Guide to the Galaxy from 1978. Many of you don't even probably know that movie. Okay, whenever you look at this, one of our first questions or one of our first focuses that we're going to take is big. How big are these objects that we find in space? Well, what I'm going to do is I'm going to give you a little video here. It's going to take a few minutes. Please watch the video so that you can actually kind of see, I'll turn it up a little bit, how big things actually are. This is going from the smallest to the largest. as you can see, the universe is really big. We went from the smallest even things below an atom up to 10 to the 27th power of the observable universe. So getting a sense of scale and being able to apply it to something that in everyday life, you can see that's just not going to be possible. So, all right, first thing I want to look at here is whenever we start comparing, we're going to start with, of course, the planets. As you can see here, this is a comparison of size of the planets. Okay, this is not the distance, this is just size. So if you were to put them next to the sun, this is about how big each planet would be in comparison with one another. Here's a better comparison of just the inner planets themselves. Of course, the top left, or the back left, would be, of course, Earth. Venus, you can see, very comparable in size. Sometimes why Venus is called Earth's twin. The front left there is Mars, and the bottom right is Mercury. Here we're going to look at the outer planets. Of course, back left is Jupiter. Back right is Saturn. Then you have Uranus in the left there, Neptune to the right, and then, of course, these outer planets you can see in comparison with the inner planets, as we're seeing in this diagram. So after you get done with that, now let's go ahead and compare the size of the planets to our sun. You can see that Earth is very, very small. I'm going to show you another image here just to see how big it actually is. But you can see that as in comparison to our sun, the planets are relatively small. Here you can see the size of Earth compared to the size of our sun. The little things that you see coming off there or off of the sun are called solar flares. Very, very detrimental, so we'll be talking about those, of course, later in the course. Here you can see that you can fit about 11 Earths across the size of Jupiter. Jupiter is just a massive, giant planet. Okay, sometimes they are typically called Jovian planets because Jovian means Jupiter-like. So that's another word for the gaseous planets. And of course, the inner planets are called terrestrials. Here's North America compared to the Great Red Spot, which is nothing more than sometimes compared to a giant hurricane. So you can see that we would be basically swallowed up by that giant hurricane. Within that Great Red Spot itself, I think you can fit almost 2 Earths. Here's the size of Earth. Well, 6 Earths compared to just to the rings of Saturn. You can see that. What's really unique about these rings of Saturn is, yes, they look monstrous, but they're very large and expansive, but they're only meters thick. They're very, very thin when looked at from the side. So very unique to see that. Here's 4 largest asteroids as compared to North America. Okay, you can see that these asteroids, sometimes you can see how they get their terms potato-like. But of course for the far left one there, which is Ceres. But you can see that they are very, very large. Now this next image is awesome because there's a comet. That's a comet as compared to the size of the city of Los Angeles. So you can just imagine how catastrophic it'd be to be bombarded by that large comet. So that's what I'm saying. You can't get a sense of scale until you start seeing these images where they compare them. It's really quite fascinating, actually. But then whenever you start taking our sun and looking at our sun, you can see in the bottom left there, it's very small compared to the red giant Betelgeuse, Antares, Rigel, Aldebaran. The sun is sometimes considered an average star. It's actually on the small end of average whenever you really look at it. Okay, so that concludes the lecture on the how big section. Now we're going to start looking at astronomical distances. And whenever you start talking about astronomical distances, the first thing you have to do is, remember I told you there was going to be extremely large units or large numbers. So what we've got to do is we've got to take those large numbers and shrink them down into another unit that basically is something we can get a grasp of and handle. Okay, so whenever you start looking at this, you're starting to look at the cosmic distance ladder. And these are ways that they measure distances to objects. We can't use the simple methods that you think of here on Earth, where it's like, okay, let's get out get out a ruler and measure it. Let's get out a meter stick and measure it, or a tape measure. That's not the case here. Okay, what you're going to have to do is you're going to have to use math and some other processes to measure these distances. We'll be talking about those later in the course, but what I really want to focus on is the first unit of measurement. The first unit of measurement that is specific to astronomy is the astronomical unit. Whenever you start talking about an astronomical unit, sometimes abbreviated the AU, commonly abbreviated the AU, 1 AU is actually equal to 150 million kilometers, okay, or 93 million miles. Of course, we tend to use kilometers in the aspect of science, but whenever you start talking about this, the reason that we come up with that number is that's the average distance from the sun to the earth, okay? We'll get into that a little bit later. So, whenever you start looking at the actual distances to the planets just in themselves, the AU is the commonly used unit of measurement, okay, or the unit that's attached to it. So whenever you start talking about distances to planet, you're always going to say like 1 AU, 2 AU, 5.2 AU, and that's what we're going to be using there. Well, as you can see, the distance to Earth is 1 AU, Mars is about 1.52, Jupiter is about 5.2, Saturn 10, and so on and so on. You can start to see here where these distances become exceptionally large. So of course, whenever you start getting into larger and larger numbers, what you want to end up doing is you want to get another unit that basically is going to break it down. But we're just going to focus on these distances right now. Okay, so looking at distances here, you look at this is the distance between the Earth and the Moon. It doesn't look too far, but watch what's really cool about this. You can actually fit, if you put every planet up against each other, you could fit all of the actual planets within there with about 5,000 miles to spare. That is so cool. The distance to the moon is about 385,000 kilometers, okay, or 240,000 miles roughly. Okay, so whenever you start looking at this, that's a long way just to our moon. Okay, so just imagine the distances to these planets that you're talking about. It's crazy. All right, so now that you've got, a sense of some distance, the last thing we're going to cover is basically how fast. Now, whenever you start talking about this, of course, it's going to start throwing everybody off because this is where the concept of look back time and all that comes into play. So we're going to go ahead and progress through this. Whenever you see the stars in the night sky, the ones that you can see with the naked eye are all those that are basically in that circle, okay? Whenever you start looking at much more distant objects, if they're so dim, the naked eye can't pick them up, but of course we can see them with telescopes, okay? So whenever you start getting to distances where you get up to hundreds of thousands and millions of astronomical units, you're like, oh man, I got all these zeros back. So what do you want to do? Is you want another unit of measurement, and that's the light year. The light year is a unit of distance, not of time. It is a unit of distance. We're going to go ahead and use 300,000 kilometers per second as the speed of light. So this is the distance that light would travel in 1 year. So what is that basically telling us? Okay, whenever you start looking at the light from the sun, that light that comes from the surface of the sun actually takes 8 minutes to get here, okay? So that's 8 light minutes. Whenever you start looking at all of the light coming from these distant objects, it's basically coming and traveling through space at a constant speed, the speed of light. So with this, we can actually use it to determine an astronomical distance, very, very large distances, okay? Now, here's what's really neat. Whenever you start to look at this, basically every time you see the light from a distant star, either with the naked eye or through a telescope, you are always going to be looking in the past because that light came from that object And however far away that object is, that's how old that light is that we're seeing. An example would be Proxima Centauri. Proxima Centauri Alpha Centauri is 4.3 light years away from us. That is an astronomically huge number. But what you basically say is 4.3 light years, meaning that the light that we see is 4.3 years old. So every time you see it, you're actually looking in the past. So if Alpha Centauri were to blow up, boom, right now, we would not know that it's blown up for 4.3 years. Okay, so you're always looking into the past whenever we see this light. That concept is the look back time. Okay, so this is basically giving you an example right here. If Sirius were to explode, okay, we wouldn't see the flash until 8.61 years later. Okay, it would still look the normal for us. If it was, say, 8 years ago, it would still look normal to us for about 7 months. So then we would see that big flash. Everything is looking into the past. And there's the cosmological principle, okay, that we call look back time. You're always looking into the past. All right? Here you can see this is a unit of scale or a unit of distance here, just the Milky Way galaxy itself. From one edge to the other, it is 100,000 light years. So if we were on the outskirts, which we are, of one of the arms of the Milky Way, we're very close out there, as you can see, 28,000 light years from the center. It would take 72,000 light years if a star was basically over here. If the light from a star was traveling, let me go ahead and do this again. Oops, sorry. If the light left and traveled all the way over, that right there would actually take about 78,000 light years. Okay? So it would take 78,000 years. So if this thing just said, boom, I blew up, we wouldn't know for 78,000. Kind of crazy. Okay, so now, here's the thing. The thing about a light year is it has a limit because you can get up to hundreds of millions of light years. So what did we just do? We just added back a lot of zeros. So the next one that we want to do is we want to say, you know what? We can't deal with that large of a number. So we've got to break it down even more. So we use this unit called the parsec. A parsec is a unit of distance. Okay? Now, 1 parsec is equal to equivalently 3.26 light years. Now, how they obtain the word parsec is it's kind of challenging to understand. What you have is you have parallax and arcseconds. Parsec. Here's what I want you to do. I want you to take your thumb and I want you to put it out in front of you and I want you to close one eye and I want you to focus on where is your thumb. Like right now I'm looking like up against my wall. It's right below a picture. Okay, so I've got my right eye closed and now I want you to switch. What'd you notice about your thumb? I'm sure you noticed that it appeared to move, right? Well, because of that motion, that right there is what is called parallax. And because of that, we can actually use that to determine how far away a star is. So we use these angles. As you can see right here, as the Earth orbits the sun, every 6 months, we take a picture of a star. And what you notice is you notice that this star appears to move in the background stars, against the background stars. Well, by looking at that, look what we can do over here. You can get angles. You can get all kinds of angles from that. And because we can do that, we can, of course, triangulate, use the principles of triangles, geometry, and basically determine how far away that star is based on its parallax shift. Okay, we'll come back to that one a little bit more later, but I'll discuss it and we'll make sure that you guys understand how that works. Okay, this discusses it a little bit more, so that you kind of know that 1 arcsecond, you're used to dealing with angles. You're going to be like, okay, that's 60 degrees, 90 degrees. Well, an arcsecond is so small of a shift, you can get it to 1/3600th of a degree. Okay? If you were standing like this over here, right, and you were saying, I'm going to find that angle right there, this is the angle that you're looking at. We're going to draw this down. It's that's a lot crooked. But what you can do is you can find this angle coming down from there, and that's going to tell you basically how far away, because there's of course a formula that we can use we'll get to later. Okay? The next unit is a megaparsec. That's just 1,000,000 parsecs, but we're not going to be using this much in this class because now you're getting into just huge distances. But just realize that a megaparsec is 1,000,000 parsecs. Okay? Okay, so you start looking at this, and here are your actual scales. You can see, looking at our solar system, it's 0.00189 light years. You look at our sun's solar neighborhood, is 4 light years. You can look at 500,000 light years. Our local group is 4 million light years. And then our supercluster is 150 million light years. So you can see that every time you start talking about space, the numbers just don't stop. They're huge. Okay? These are the units that we use: kilometer, astronomical units, light years, megaparsecs. So you can see we use special units for the objects that we're talking about. And this will come to you. You're going to be basically focusing on a lot of this, and you'll understand it as we go throughout the course. Okay, here's what I want you to do. I want you to kind of go ahead and listen here. Let me go back to my oops, I gotta get rid of that. Okay, what I'm going to do here is we're going to go ahead, get rid of this, and I'm just going to start this video. Attempt to start this video. Okay, here we go. What's wrong with Han's statement in this video?
Han Solo. I'm Captain of the Millennium Falcon. Chewie here tells me you're looking for passage to the Alderaan system. Yes, indeed. If it's a fast ship. Fast ship? You've never heard of the Millennium Falcon? Should I have? It's the ship that made the Kessel Run in less than 12 parsecs. I've outrun Imperial starships. Not the local bulk cruisers, mind you. I'm talking about the big Corellian ships now.
Okay, so what was wrong with Han's statement in this video? Well, I'm sure that you actually heard him say that the Millennium Falcon made the Kessel Run in 12 parsecs. Well, here's the thing. He used a parsec as a unit of speed. It's a unit of distance. It's a common misconception. It's even in the new Star Wars, which is kind of frustrating that they still say parsecs and they're using it incorrectly. The parsec is a unit of distance, and you please remember that. Okay, so what this does is this concludes our lecture for this topic. The next lesson we're going to be looking at is basically starting to observe the night sky and learn more about where we are in our place in the universe.